So today for section 11.3, we are going to start taking a look at matrices. So a matrix is a rectangular array used to organize work or numbers. Typically a matrix is written with either a set of parentheses or more commonly a set of brackets. So if you look here, this rectangular, what looks like a box here is a matrix. A, B, C, D, E, F would be the entries in the matrix. And then if we talk about the size or dimension of that matrix, it is always the number of rows by the number of columns. So this matrix right here has 2 rows and 3 columns, so we would call this a 2 by 3 matrix. One major application that we're going to discuss today for the use of a matrix is to organize and then solve a system of equations. So if you take a look at this system of equations, that is 3 variables, 3 equations. So we have x, y, and z in 3 separate equations. This would be really tedious to solve by hand. And when I say by hand, I mean using elimination or substitution. So if we can take this system and organize it as a matrix using the coefficients of the variables and what the equation is equal to, once we have that system organized in a matrix, then we can operate on that matrix and essentially go through the solving process we would if we were to try and solve this algebraically. So if I take this system of equations and take the coefficients of the left side, so take a look at the first equation, x plus 2y plus z equals 5. And if we look at the first row of the matrix, we have 1, which is the coefficient of x, 2 is the coefficient of y, 1 is the coefficient of z, and 5 would be the numerical value that the equation is equal to. Same thing for equation 2. The only thing is this should be an equals here, a small typo. And then same thing for equation 3. That matrix is called an augmented matrix, and what that specifically means is the last column is an answer column. So the 3 columns on the first 3 columns of the matrix are our coefficients of our variables, and then the last column is our answer column. So sometimes what you'll see in an augmented matrix is either a dashed line that kind of separates the coefficients from the answer, or a solid line there. And that also shows that we're dealing with an augmented matrix, which will definitely be necessary to understand once we get into using matrices to solve equations. So before we get into the actual process of using a matrix to solve a system of equations, we have to talk about a few different allowed operations for a matrix row. So if you look at the elementary row operations, what they're called, I can take a row and multiply each entry in that row by a constant, which will essentially be me making that row larger, or if you connect it to the equation, that'd be me multiplying an entire equation by a constant, which doesn't change the values of the variables, but multiplying by a constant will definitely be helpful once we get into solving. So that's an operation that I can perform. I could also interchange 2 rows, replace row 1 with row 2 and row 2 with row 3, and just kind of move rows up and down our matrix, which again doesn't change the value of our variables, but it's just something that will be helpful at times when we start solving systems of equations using a matrix. And the last one, which is kind of one of the bigger steps that we'll need to understand, is how to take 1 row, multiply it by a constant, and then add that to another row. And essentially what that is me scaling 1 row or 1 equation by a number and then adding it to another row, which would be me kind of using the elimination process of solving a system, but we'll be doing it all working with coefficients, which makes the computation part a lot easier to deal with than constantly writing these 3 variables and 3 equations. So using a matrix to organize our system will be very helpful when we start trying to solve for, in this case, x, y, and z in our system. And one thing I want to mention before we move on to writing augmented matrices for systems of equations is you do want to make sure that your equations are in standard form. So if you look at this system here, just wanted to definitely mention that fact. We see that all three equations go in the same order: x, y, z equal to a single number. That is going to be key to make sure that our columns are, like in this matrix, the first column 1, negative 1, 1 are all coefficients of x. Second column coefficients of y, third column coefficients of z, and so on. Because when we start working with these matrices and trying to solve a system using them, we do want to make sure that our columns are all consistent with what variable we're dealing with. And then if we follow these row operations here, we'll be able to do the same process we would solve a system by hand, but using a matrix, which kind of streamlines the computation part, and you don't have to, again, like I said, rewrite all the equations every single time. So we take a look at the first example. We want to take this system of equations and write an augmented matrix. So we have a 3-variable, 3-equation system. So first thing I want to do is identify what size matrix I'm going to be dealing with. So the number of rows are there are 3, and there are 4 columns, so coefficient of A, B, C, and then an answer column. So if I draw a 3x4 matrix, my first row will be 3, and then negative 1, and then negative 4 for the coefficient of C, and that's going to be equal to 3. Now again, like I said, that dash line or solid line is clear notation that we're dealing with coefficient on the left, and that 3 would be a value or an answer. If it's not there though, that is also some notation you'll see at times. But we'll know from the context that we're dealing with a system, so we'll know that that last column is our answer. So then our second row is going to be 1, 2, negative 3, and 9, and our third row will be 2, negative 1, 2, and negative 8. So that's just taking a system, first ensuring that we're in standard form, or that our variables are in the same order, and then we are going to write the coefficients and the answer in a matrix. For the second system, if you take a look, the first equation is 12x minus 11z equals 13. So on the surface that looks like we're dealing with 2 variables, but again, if you look at the entire system, you'll see that the second equation has a y variable. So we're going to need at least we're going to need to include a placeholder for our y variable in our first equation. And so we're going to be dealing with a 2x4 matrix, 2 rows, 4 columns. So the first row will be 12, and then again, I want to have a placeholder for my y variable because my second equation has a y variable. So it'll be 12, 0, negative 11, and 13. And then my second row should be 6, 6, negative 4, 26. So that is an augmented matrix for that system of equations for number 2. For the next 3 examples of the notes, we're going to be using an augmented matrix to solve a system. So if you look at this first system here, number 3, we are going to first express this as an augmented matrix. So the size of this matrix should be a 3-row by 4 column. And then taking a look at the equations, I want to make sure that I put the correct coefficients in the correct place. So my first row should be 1, 0, 1, negative 2. Again, there's a 0 there because it's a placeholder for my y variable. My second row should be negative 3, 2, 0, 17. The 0 in that second row represents the z variable that is not present in the equation. And then my third row should be 1, negative 1, negative 1, negative 9. So this is the augmented matrix for that system of equations. And now, concept here, before we get into the row operations and how we use them, I want you to think about what we're trying to accomplish here. So if I draw over to the left here, I'm going to draw a matrix here. So I'm going to draw a 3x4 matrix just to kind of represent what's happening here. So if you look at what I drew, I wrote 1, 0, 0, and I have a dash line A, and then the second row is 0, 1, 0, B, the third row is 0, 0, 1, C. What that represents is a matrix in what we call reduced row Echelon form. We'll talk more about the name of that, but the concept here is if I can get the first row, or any row really, to have 1 as its first coefficient, that represents my x variable, so that's 1x, and I can get the second entry in that row and the third entry in that row to be 0 using my row operations, and I'll demonstrate how to do that. And then on the right side of that dashed line, a number, what that would tell me is I would actually have my solution for x. So x would be a in that case. And again, in the problems we're going to be working with, we're going to have a real number there, but concept-wise, if I can get my matrix to look like that in terms of everything to the left of the dash line is 1, 0, 0, 0, 1, 0, 0, 0, 1, what that shows is we have a solution for x, a solution for y in the second row, and a solution for z in the third row. So in that matrix I drew, the answers would be x equals a, y equals b, and z equals c. So what we're going to do is, for the next few problems, work with our matrix, use those row operations we talked about to rewrite my matrix so that I can find solutions for x, y, and z without having to rewrite the system a bunch of times over and over again. We could actually just work all within our matrix following those operations and find our solution. So the first thing I'll say off the bat is there's no one direct approach to get there. As long as you work within those row operation rules, meaning you scale a row by a number, you replace rows, interchange them, or multiply a row by a number and add it to another row. As long as you do those things correctly, you should be able to get to the solution. Now, the path you take to get there, or how you approach the system or how you approach the matrix, might differ. So the steps I'm going to do aren't necessarily the only steps or the right steps, but it's just me trying to work with the numbers that I have in terms of my coefficients to find my solution. So again, your steps might look a little bit different than mine at the beginning, but as long as you follow the operation rules and make sure you don't make any arithmetic mistakes, which is very common with matrices. Sometimes we have a tendency to subtract wrong or add wrong, or be a little bit careless there, and if you do that, then if your coefficients are off, then your solutions to your variables will definitely be wrong. So for sure, be careful here. So again, I'm looking at this matrix. I'm trying to start getting other coefficients to be 0 so that I can find solutions. So the first thing I would do, actually, and this is kind of how I'm going to write it, I'm going to draw a little arrow, and what that arrow is going to represent is essentially I'm going to take this matrix and I'm going to perform some operation on it, and then I would get a new matrix. So I'm going to take row 3 and I'm going to subtract row 1. And I'll show you what that does in a second. And then I'm going to take row 2 and I'm going to add 3 times row 1. So the rows that I'm going to change are row 3 will look different and row 2 will look different from this matrix to my next one. So the first thing I'm going to do is rewrite my first row, since I'm not changing that one, and I would get 1, 0, 1, negative 2. And then to get my second row, take a look at the operation that I said. I'm going to take row 2 and I'm going to add 3 times row 1. So the way I think about that is my first entry for row 2 is negative 3, and if I add 3 times 1, which is the first entry of row 1 multiplied by 3, I get 0 for my first entry of row 2. So I took 1 in the first row, multiplied it by 3, and added it to row 2, which changed my first entry in row 2 to a 0. And then I would do the same thing through that entire row. So make sure whatever you do to a row, you do to that row throughout the whole thing. And then if you want to do something later, you'd have to do it in another step. So then to get my second entry, I took 0 in the first row, multiplied it by 3, which is 0, and added it to the second entry in row 2, stayed 2. And then if I took 3 times the third entry in row 1, which is 3, and added it to 0, I get 3. And then if I do the same thing for the answer, I would get 11. So negative 2 times 3 would be negative 6, added to 17 is 11. So if you look, what I did to row 2 was I quote-unquote eliminated my coefficient for x. So now my second row only has y, and z equal to a number. So that's essentially what you're trying to do. You're trying to look at the system, look at the matrix, try and perform some operations so that you can begin taking a row down so that it only has a 1 as an entry in one of the variable spots equal to a number. So then for my third row, I take whatever I have in the third row and I subtract the entry from row 1. So first entry would be 1 minus 1, which is 0. And then I would take negative 1, which is my entry in row 3, minus the entry in row 1, which is 0. So negative 1 minus 0 is negative 1. And then negative 1 minus 1 from row 1. So I'm in the third column, row 3. So I took negative 1 here and subtract 1 in row 1. I would get negative 2. And then for my answer, I should get negative 7. So again, I performed 2 operations to my matrix, and what you'll see is I changed my second row and I changed my third row based on the operation that I identified. If you take a look at what I have now, I'm looking at row 2 and row 3, and because both of those have a 0 in the X column, I'm going to try and operate with those two and see if I can eliminate or make another column entry 0. So the step I'm actually going to do is I'm going to take row 2 and add 2 times row 3. So the first thing I like to do is, draw an arrow, identify what I'm going to do to the matrix to get to the next matrix. And then because I'm not changing row 1, I'm going to just rewrite row 1 and leave it alone. Try not to do too many operations at one time because then it's kind of hard to keep track of. For me, I'm only going to usually do probably 2 at a time, and then see what I have from there. And you're going to write the matrix a few times over, but it's better to be careful, especially at the beginning, so you get a little more comfortable. So what I'm going to do is take row 2 and then add 2 times row 3. So my row 2 would become 0 is the first entry because 2 times 0 is 0, added to 0 is 0. And then if I take 2 times row 3, that makes this entry negative 2. And if I add it to row 2, I should get 0 as my second entry. And then 2 times row 3, which would be negative 2 times 2, which is negative 4, added to 3 should give me negative 1. And then 2 times negative 7 is negative 14. Add to 11 gives me negative 3. And then I'm going to leave row 3 just how it was for now. And that would be my next operation for this matrix. The next thing I'm going to do is exchange row 2 and row 3, just because if I look at what I have in row 2, I have 0 for x, 0 for y, and z. And not that you have to exchange them, but doing so would actually kind of start to get it in that form I mentioned at the very beginning of the problem. So if I do that, I would rewrite my matrix, and I would replace those two. And then the next thing I would do is take my new row 2 and multiply it by negative 1. So what I would get if I followed those two operations would be 0, negative 1, negative 2, which was row 3, which is now row 2. And then what was row 2, I multiplied it by negative 1 and replaced it where row 3 was. So I have 0, 0, 1, 3. And now right here, I'm going to pause for a second and look at what I have. Based on that third row, what I found out is z should be equal to 3. So I have a solution for z. So from here on out, I don't want to do too much to row. I don't want to do anything to row 3, actually. I might use it, but I don't want to change row 3 because that is a solution for z. So the next thing I'm going to do is I'm going to take row 2 and I'm going to add 2 times row 3. So what that's going to do here is it's going to allow me to take row 2, and if I double row 3, that makes my third entry 2, added it to row 2 would make that 0. So if I look at what I have, I'm going to keep row 1 exactly the same for now. And then row 2 becomes 0, negative 1, 0, negative 1. And the way I got that is by taking the entries in row 3 and doubling them, and then adding them to row 2. So you could check the math there. What that gives me is 0, negative 1, 0, and then -1 for my value, and then I'm going to keep row 3 exactly the same. So you can see I'm pretty close to being done with solving the system. The last thing I need to do is, if I look in row 1, if I can eliminate that third entry in row 1, make it a 0 somehow, then I would have 1, 0, 0 in row 1, which would give me a solution for my x variable. So the way I could do that is, if you look at row 3, if I just take row 1 and I subtract row 3, that would give me what I'm looking for there in row 1. And then the only other thing I would do is, in row 2, I would multiplying row 2 by -1 would give me a row that is non-negative anymore. So the reason I would do that again is, the second entry in row 2 is -1, so if I multiply by -1, it would be +1, and then I would get my solution for y. So performing those two operations, what that would give me is row 1 would become 1, 0, 0, -5. So take row 3, which is 3, subtract it from -2 gives me -5, and then row 2, which I multiplied by -1, becomes 0, 1, 0, 1, and then row 3 I left alone. Now if you look at the matrix I have, again, went through a few different steps, a couple different processes using my row operations. What I have now is my system is solved. So 1, 0, 0, -5 is actually the equation x plus 0 plus 0 equals -5, or x equals -5. Second row would be y equals 1. Third row would be z equals 3. So one way that I could write that solution would be xyz is equal to, and it looks like obviously a set of parentheses, but -5, comma 1, comma 3, and that would be the solution to the system of equations. If you were asked to verify or check, what I would do is, take the values for x, y, and z and plug them in, and make sure that they work in all three equations. So it needs to verify all three equations are equal left side and right side in order for that to be a solution. We're not explicitly asked to check, but that is definitely something that you should at least make sure you do at times, even if it's just mentally. Just take a look at the values you have for x, y, and z, and just make sure that they work for our variables in our system. So that is the process of using a matrix or an augmented matrix and row operations to solve a system. So we're going to do a similar process for our next example, and just practice the idea of expressing a system as a matrix and then performing row operations to solve a system. So the first thing I would do is, one, check that these equations are in the same form, xyz, 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 so we're good there. So if I wanted to write this system as a matrix, here's the matrix that I would get. So first row would be 1, 1, 1, -4, those coefficients x, y, z, and there's my second row and third row. So just make sure your coefficients are obviously in the correct place in terms of their column, and then also that they have the correct sign in front of them. So there's my augmented matrix for this system of equations, and the goal here is to perform these operations and try and find the solutions for x, y, and z. So again, there's no one way to get it done. There's no direct process every time. But for me, if I can eliminate a variable, and when I say eliminate, I mean make the entry 0 in a column. So if I can do that in a row, then I'll be on my way to getting one entry per row equal to a number. So the way I'm going to do it here is, what I'm going to do first is I'm going to take row 2 and subtract 2 times row 1, and I'm going to take row 3 and subtract 4 times row 1. So thinking about why I would do that, if I take row 2 and subtract 2 times row 1, that'll make my first entry in row 2 0, because I would take 2 minus 2. And then if I do row 3 minus 4 times row 1, that would also make the first entry in row 3 0. So then, row 2 and row 3 will only be dealing with x and y, and then maybe I can use those two together to eliminate or make another entry 0. So let's just work with those two operations. So row 1 is actually going to stay untouched. So leave that one alone for now. So if I take row 2 and subtract 2 times row 1, so double row 1 and then take it away from row 2, it should give you 0, -5, -1, 7. So 2 minus 2 times 1 is 0, first entry. -3 minus 2 is -5. 1 minus 2 is -1. And -1 minus -8 would be +7. And then in row 3, I would take 4 and subtract 4 times row 1, which makes that first entry 0. And again, you could check the math there all the way through and just make sure that I have the correct values in each row. And that's just me following the operations that I identified in between matrices. That's why I think it's a good idea to draw maybe an arrow or something showing I'm going from that matrix to the next one. And it's a good idea to kind of put the operation in between just so you can have as a reference. So here's my new augmented matrix. I haven't changed the values of my variables. I've just been working to eliminate variables or make entries in each row 0. So now, looking at what I have, I'm going to try and figure out a way that I can make another entry 0 in one of my rows. So what I'm actually going to do is take row 3 and subtract 7 times row 2. So what that'll do is if I take row 3 and subtract 7 times row 2, I would get one of my entries to become 0. And the entry that would become 0 would be, before I do that, again I'm going to rewrite the matrix, keep the first row the same for now. And actually the second row is going to stay the same because I'm only changing my third row. So I'm going to take row 3 and subtract 7 times row 2. So I take row 2 and multiply it by 7 and then subtract that from row 1. I would get 0 for my first entry in row 3. I would get 37 for my second entry. So I'm doing 7 times -5, which is -35. So -2 minus -35 is +37. Actually, not 37. It should be 33. And then 0 for my third entry, and then 0 for my answer. So looking at that equation, I have 0, 33, 0, 0. And if I take that third row and I multiply it by 1 over 33, what that'll do is make my third row 0, 1, 0, 0, which would allow me to find the value or the solution for my y variable. So I'm going to rewrite the matrix and then just have my third row be 0, 1, 0, 0. So now I have a row of what I was looking for. I have a solution for my y variable, and I'm going to try and continue to work that process to get my other two rows to have a single non-zero entry so I can solve for that variable. So the next thing I'm going to do here is try and take row 2 and I'm going to subtract 5 times row 3. So I take row 2 and subtract 5 times row 3. Actually add 5 times row 3. Because if I take row 3 and multiply by 5 and then add it to row 2, it would make my second entry in row 2 0. So if I look at this, I'm going to keep row 1 the same for now. And then row 2 would become 0, 0, -1, 7. And then row 3, I would keep exactly the same for now. So you could see now that in row 2, I'm really close to having my solution for z. The only thing I would need to do is multiply that entire row by -1 so that I have a positive coefficient for z equals -7. So I'm going to do that, but I'm also going to try and eliminate or get another entry to be 0. So the other thing I'm going to do is take row 1 and I'm going to subtract row 3. So let's roll with both of those operations. So again, my first row is going to become, so I'm going to take row 1 and subtract row 3. So it becomes 1, 0, 1. And then the answer actually doesn't change, should be -4. And then multiply row 2 by -1. gives me 0, 1, or excuse me, 0, 0, 1, negative 7, and my third row is 0, 1, 0, 0. So the last thing I have to do in order to solve this system is I need to make my first row be 1, 0, 0. So I need some way to eliminate that third entry in row 1. So the way I'm going to do that is I'm actually going to take row 1 and subtract row 2. So if I do that, my row 1 would become 1, 0, 0, and then I have negative 4 minus negative 7, which is actually positive 3. And then my other two rows can stay exactly the same. And the only other thing I did was exchange the place of row 2 and row 3, just because if I look at my matrix now, my first row gives me my solution for x, so x plus 0 equals 3. And then my second row gives me my solution for y, and my third row gives me my solution for z. So my solution xyz would be 3, 0, negative 7. And then if you wanted to verify that, obviously you can take those values for x, y, and z, plug them into the system in all three equations, and make sure that they work in all three equations. And for our last example today, we are going to take a look at another system of equations. And this one's going to be a special case. You wouldn't know it's a special case by looking at the system necessarily, but I did want to tell you that up front, just because when we start working with our matrices, you'll see something noticeable happen, and I wanted to kind of preview that for you so you'd know that there is something slightly different here, and we'll talk about kind of how to handle it. So the first thing I'm going to do is I'm going to express my system as an augmented matrix. So use the coefficients and the answers on the right in my matrix. So we have a 3 by 4. And then, like I said before, there's not one direct or perfect path to take, but I'm looking to try and eliminate an entry in a row or more than one row at a time. So if I can do that, then I'm working my way towards getting a single entry in an equation, or excuse me, a single entry in a row equal to a number. So what I'm going to do actually first is I'm going to try and eliminate an entry in row 2. So looking at row 2 and row 3, I see that if I take row 3 and multiply it by 4, and then subtract that from row 2, my third entry in row 2 should become a 0. And then the other entry I think I can eliminate or make a 0 is if I take row 1 and add 3 times row 3. So if you notice, 3 times row 3 would give me a negative 3 in my third spot. If I add that to row 1, I would get that entry to become a 0. So my first row would become, so 3 times 9 in the third row is 27, added to row 1 would give me 31. And then 3 times negative 2 down here is negative 6. Add that here should give me positive, 3 times negative 2 is negative 6. Add it to negative 3 gives me negative 9. And then 3 times negative 3 is negative 3. Added to 3 is 0. And then 3 times 3 is 9 plus 2 is 11. So my first row becomes 31, negative 9, 0, 11. And then in row 2, I'm going to subtract 4 times row 3. So 4 times row 3, 4 times 9 is 36. Subtract that from 5, I get negative 31 in my first entry. And then if I take 4 times row 3, which is negative 2, times 4 is negative 8, and I add that, subtract that from 1, I get positive 9. And then if I take 4 times row 3, which is 4 times negative 1 is negative 4, and I subtract that from negative 4, I get 0. And then 4 times 3 is 12, and I subtract that from 1, and I get negative 11 for my answer. And then I'm going to keep my third row exactly the same. I'm not going to touch it yet. So that's me trying to eliminate the third entry in rows 1 and rows 2. And then if I look at row 1 and row 2, this is why I kind of prefaced that this might be a special case, is looking at what I have, if I added row 2 and row 1 together, something specific is going to happen here. So if I do that, my matrix becomes 0, 0, 0, 0 on the top row, and then I'll leave the other rows alone for now, and let's talk about what's happening here. In that first equation, or that first row, what I have is the coefficient of all three variables is 0, and the answer is 0. So what that tells me is there's something special happening here, which means my answer isn't necessarily, I'm not going to be able to find basically a real number value for x, y, and z. There's something happening here. So let's think about what's happening in that first row. I have 0x plus 0y plus 0z equals 0, which means 0 equals 0, or the left side equals the right side for any values of x, y, and z. So in terms of what's actually happening in this system, there's a specific way that we would answer this question, and that would be there are actually infinitely many solutions. So the idea is any values for x, y, and z in that first row would work, because if I plug them in, I should get an identity. So there are infinitely many solutions, and like I said, a special case here is because all three variables had a coefficient of 0 equal to 0. Now there is a possibility for another type of special case, which if you think back to solving systems or solving equations in algebra, we really have like an infinitely many solutions option and a no solution option. So consider, for instance, this matrix here, and I'm just going to kind of make one up here. So let's say the first row is 0, 0, 0, 1, and the second row could be 2, 4, 6, 8, 1, 7, 9, 11. So what happened here, let's say I was working with a system and I got the coefficients of my three variables x, y, and z to be 0, but the answer is equal to 1. And what that means is, in terms of everything on the left, 0 plus 0 plus 0 is 0, and I would get 0 equals 1, or if I got all three coefficients to be 0 and the right side to be any number other than 0, since that would not be an identity, this would be actually a no solution to this system of equations. So using a matrix, it's not super clear what the special case looks like when solving, so that's why I wanted to definitely talk about these two examples. So if you get all three variable coefficients to be 0, but the right side is also 0, meaning you're dealing with an identity, you'd have infinitely many solutions to that system. And if you get all three coefficients of your system to be 0 equal to a non-zero number, like in row 1 of this additional matrix I drew, that would be a special case where the solution to the system is no solution, actually. So general process here, a matrix is a really nice way to organize a system, and then once you get comfortable with the operations or the process, it's definitely a little bit more computationally convenient to use a matrix to organize your data and eliminate variables or get coefficients to be 0 to find the solution to the system of equations.